Well, thank you everyone for joining today. I see there are people connecting right now, but this topic is very interesting, like all the topics that we cover in this technical webinar. And I do want to stay on time as much as possible. So, what do you say, Bob, if we just start the webinar?
Sure. Yeah, let's see if we can go.
So let me introduce Bob Johnson. I believe many of you are already familiar with him. I honestly, Bob, I think you are the person to cover
Uh,
today's topic. So
thank
for
you,
all of
Barbara.
you who are not familiar with Bob Johnson, he has been working in hazardous location with design in installation of electrical and mechanical equipment for I'm gonna say almost 40 years now, Bob.
Yeah, yeah,
Yeah.
yeah. Actually, this year, 40 years. So,
Yeah. So you have seen a few things in your time.
yes, I have.
Yeah. Bob is also the president and owner of Source IEX, who is a distributor partner for GMI here in Texas. And he is also instructor for the COMPEX and the COPC scheme, which will be for ATEX and IECEX for competence of personnel working in hazardous locations environments. Um, he also carries or does inspections for customers. Again, everything in hazard locations. So I am very happy that you are here with us, Bob, to cover today's topic on explosion proof fundamentals of explosion proof areas.
You bet.
Um, and for all of you who are not familiar with me, I am Barbara Vasquez Isla. I am part of the GMI team in the Americas. I support customers in North America and South America, selecting the correct or the best option for intrinsic safety applications, as well as functional safety solutions. Mhm. Before we go into today's topic, let me give you guys an overview of who is GMI. Also, let me just highlight a few things. This webinar is being recorded. We do want to hear from you. However, you can see that your microphone is being muted. So please use the question chat, even for comments or just to say hello. So please feel free to chat with us. We'll be here checking those comments. As well, you will get an email if you stay more than 75% of the time of this webinar. You will get an email with your certificate of attendance and the presentation, so you can review it later on. But yes, so I was saying GMI, if you are not familiar with this company, is a company that designs and manufacture interface devices specifically for intrinsic safety and functional safety applications. So pretty much IS barriers and safety relays with SEAL up to SEAL 3. These devices are utilized heavily on emergency shutdowns applications, fire and gas systems, high integrity pressure protection systems, and they communicate with the PLC and DCS, right? The safety PLC and DCS for the process industry. So we're in oil and gas, petrochemical, pharmaceutical applications. We are an Italian company and we have a presence in all continents. On the next slide, we'll see that we do have a few offices all around the world, but we work very closely with our local distributors, such as Source IEX, all over the world. So we want that way we can be close to you, close to the user, close to your application. Our products are all manufactured in Italy. We have a state-of-the-art facility, and quality is very important for us. It's imperative for us, and is a foundation of our company. The high quality of our products. Because of that, we fully test every single product before it leaves our facility. That also allows us to offer you, the customer, a 5-year warranty in all our products. As an Italian company, we do carry the European approvals, and as a global company, we carry global approvals. So you can see if many of our products, ATEX, IECEx, UL or FM for Canada, United States, you will see some of them in Metro, PESO, and many other international certification needed for specific countries. We also have marine approvals for offshore applications, and TUV for the functional safety.
You have a lot. For a
Yes,
small company,
yes.
you have a lot.
When you look, and one of the things that I like is that the product will have all of them. So you don't have to choose like, oh, for this product, I need to buy this part number that carries this certification. And for this other project, this other certification. So the same item, right, Bob, will have
Yeah.
everything on the side so you can see it there.
Yeah, and Barbara, let me interrupt you because right now, the last couple of days, I've been doing an inspection, and there's a particular manufacturer that has an option for an ATEX version, an IECEx version, a FM North American version, and a different. And if you don't order or at the right suffix, it only comes with the label that is appropriate for or with that particular certification. And unfortunately, in this case, there was a transposition of a single letter in the ordering code, and the items that they ended up getting were marked ATEX, and this is a project that they actually require IECEx. Same product. Unfortunately, now we've got to figure out a way to get that rectified, but that's fortunately we don't have that problem with your product line. So
True, true. So it does come handy having, all those different certification on the side of one part number, one product.
just makes it
So
difficult to read.
you need to have your glasses, absolutely.
Yes.
All of us,
Yes.
we need to have our glasses there.
Yes.
So this is a snip of our product portfolio. Like I was saying, intrinsically safe galvanic isolator barriers, safety relays, signal conditioners, power supplies, hard multiplexers, surge protectors. All of those will have up to SIL 3. We also have the thermocouple multiplexer, which comes very handy when you want to monitor temperatures in remote locations. And we have our X1 series, which is a termination board solution for marshalling panels. It is very compact, so allows a high density of signals in a marshalling panel. If you want to learn more about the GMI products, please feel free to send me an email and we can organize a Teams call later on. And I think I didn't mention it, but the company GMI has been in the supporting customers for more than 30 years, probably 40 by now. And this is a sample of some of the customers that we have been able to partner to provide solutions for their applications. So without further ado, Bob, the microphone is yours.
All right. Well, thank you, Barbara. And again, thank you everybody for joining us. We've done this webinar before. We've done webinars on different topics, and this is one we hadn't done in quite some time. And I realize many of you are probably fairly experienced in the EX world. So a lot of probably what I'm going to be talking about today is already stuff that you may already know. But I also realize that it's always good for refresher in some cases. And certainly we may have some new people that really are just starting out in their EX journey, and we want to don't want to forget, because even though some of this stuff today is fundamental, it is really the important stuff that we need to know. So we've tried to highlight, if you will, what are the key things that we really have to understand on the fundamentals of EX equipment, explosion protection, and kind of put it hopefully in an easy to understand methodology here. So in effect, and this really, regardless if you're doing a project around ATEX or IECEx or North American class division, The explosive atmospheres doesn't really change. How we categorize them does, but the actual physics of the environment doesn't really change. And so we more or less have in the world, it's broken down into three different major categories, if you will. We will have gases and vapors, the mists, we'll have combustible dust and ignitable solid particles. If you notice that the gases, when we're talking about the gases, that's really the vapor gases. It's not the liquids. Liquids generally are not the ignitable portion. It's when they start off gassing and becoming a vapor, that's when we start having a combination of fuel to air. That's when we really have problems. So typically liquids themselves are not combustible or ignitable, but when we start adding air into the equation, which we do, that's usually when we start having problems. Combustible dust, we don't necessarily think about this all the time, but things like grain elevators. We might have heard of certainly coal mines, places like that. But again, places like grain elevators or pharmaceutical plants or woodworking process. Ignitable solid particles, again, that could be a clothing manufacturer where maybe we're using fibers like cotton fibers or something like that. Those can ignite based upon where they're located and how they could actually get on top of, say, a heat producing device. So all of these potentially can be what we would consider to be an explosive atmosphere. So there's an important point that we have to talk about when we're talking about liquids. So combustible and flammable liquids will produce these gases. They can be easily ignitable, and they're very dangerous, and they can spread quickly and widely. So all flammable liquids which are at or above their flash point will give off a combustible vapor. So the flash point, you might hear this term. What the flash point is of a combustible liquid is the point in which the temperature in which that gas or that liquid will start to emit flammable gases or vapors. So when we start thinking about liquefied natural gas, LNG, part of the reason why we liquefy it and put it under pressure is that we can get a lot of volume, if you will, when we liquefy it, and it's much more effective as far as transportation. When we have problems with liquefied natural gas is when it starts coming up to an ambient temperature. And typically these gases will have flammable liquids, or the flammable liquids, the flash points, generally are usually somewhere at negative degrees Celsius of some point. And they all have different ranges. But so we typically have to cool them to a certain extent to be able to turn them into a liquid. So there is a difference between the term flash point and the ignition temperature. So the ignition temperature is the temperature in which that gas or vapor will spontaneously ignite. One of the things that we talk about in some of the training programs we do is we ask the question, flash point versus ignition temperature. The flash point is always going to be below the ignition temperature of the gas or vapor. Now, combustible dust can be made up of various different types of dust. The most dangerous dust are metal dust. And the reason why they're very dangerous is metal dust can actually conduct. So therefore, obviously, if we have an electrical fault or a short, or think about maybe a plug-in socket that you might have, and if you had metal dust potentially accumulate amongst the face of, say, a standard plug-in socket, well, then all of a sudden we have a shorting situation. That short is going to create energy, then the metal dust will ignite, and then we can have an explosion. So things like aluminum dust, magnesium, those are extremely dangerous when they're in a dust, very, very small particle size. Then there are things like carbonation dust, which are coal, carbon black, charcoal, coke dust. And then other types, flour, grain, wood, plastics, and chemicals. So again, a lot of us in the EX world, we think primarily around gases and vapors, but there's a substantial amount of explosive atmospheres that exist in areas that you wouldn't necessarily think about, such as food processing or pharmaceutical or even grain elevators or places like that. One thing is only dust with stable oxides will not be combustible. So not all dust will be combustible. So the basic fundamental here is in order to have an explosion, we have to have more or less three different sources. We have to have a a concentration or material that's ignitable, which could be a vapor, could be a dust, could be ignitable fines, we have to have typically air or oxygen, and then we have to have a source of ignition. Now, a source of ignition is really where we start looking at all these explosion protection techniques, and we try to minimize those sources of ignition. But first, we really have to be able to identify sources of ignition in order to make a really informed decision. So, what are the ignition sources that we will find out there in industry? Well, these could be hot surfaces, such as bearings, lightning, engine exhaust, friction, obviously an open flame, any fire, cutting torches, cigarette lighters. Also mechanical sparks, grinding and cutting of equipment, drop tools, or even thermite action. These are all potential sources of ignition. One of the big ones that has really taken a lot of people that are really starting to look very closely at is certainly not just stray electrical currents, but static electricity. The buildup of electrical energy due to either non-metallic materials. We could have all different kinds of issues that could cause static electricity. And when it gets released, the amount of energy that gets actually released into the environment due to static electricity is actually it does contain enough energy to actually ignite some of the gases and vapors that you will find out there. And certainly now that we're talking about radio frequency, bringing in obviously a lot of communication devices, what does that do? How do we have to address all that? Things like telephones, transmitters, wireless access points. Certainly batteries, ionization radiation, ultrasonics, and even exothermic reactions. So when we talk about and we really start looking at our facility and say, hey, if we've got a flammable gas, we have an ignitable dust, we have ignitable flyings, and they're going to be present in some way, shape, or form, what we really should be doing is what is called an ignition hazard assessment and looking at all of these processes and potential sources of ignition that exist within our facility. And then we start making determinations as how we're going to address it. Can we remove it? If we cannot remove that process, how can we minimize it? And in that case, if we can't minimize it or remove it, then we may have to employ some sort of EX protection concepts. So just to give you an indication of some of the ignition temperatures of some of the gases and vapors that you will typically find, and this is based upon the IEC standards, but these numbers are pretty much similar, not exactly the same as per the NFPA documents, but they are very similar, that you will find that these are the ignition temperatures, and generally they're pretty hot. So it takes a lot of heat if just ambient temperature is not going to ignite these gases and vapors. It's going to take an extremely hot surface. However, that's from the ignition temperature, but we also have to take into account the electrical current that it would actually take in order to ignite it. And this is the amount of energy that we're talking about. So if we look at things like propane, it takes a fair amount of energy in the form of a microjoule to ignite it. But when we look at things like hydrogen, you notice the difference between propane of 260 and hydrogen is only 19. That's one of the reasons why hydrogen is, number one, a great source of energy because it doesn't take much energy to ignite it, but it's also one of the more dangerous gases for many different reasons. And one of them being it takes a very, very limited amount of energy in order to ignite hydrogen. So when we're now talking about going to the hydrogen economy, there's a lot of issues when we want to use hydrogen. It is an extremely effective gas. It is very efficient, but it is also one of the more dangerous gases that are out there. There's also a function that we need to know about particular gases and vapors of this minimum ignition energy, but we also, when we take into account, I mentioned to you about the explosion triangle, and we have basically we have to have a ratio of flammable gas to air. And when all gases and vapors will have some sort of ratio, if you will, or what they call a lower flammable limit and an upper flammable limit. And these upper and lower flammable limits the EIC, the most easily ignitable concentration of this, is kind of that sweet spot, meaning that in this case, with that hydrogen curve, a ratio of about 28% of hydrogen to about 72% air, that's where that 19 microjoule, if that comes into play, we're going to have an explosion. So all gases and vapors have kind of that sweet spot, if you will. And think of it this way. A carburetor in your car, it's obviously bringing in air, it's bringing in fuel. You have to have that right fuel air mixture. You have a spark with a spark plug, you have combustion. If you have too much fuel, it's too rich, you're above that upper flammable limit, or you maybe are not quite as effective, if you will. Or if you don't have quite enough gas, you're nearing the lower flammable limit. So the carburetor is basically trying to get that proper exact mixture to make it the most efficient of making sure that the amount of vapor, gas vapors, and the amount of air at that particular time when the spark plug hits is going to be a perfect explosion. That's kind of the similar concept here. Now we have some poll questions, and we did this last time, and I don't know if they worked or not, Barbara, so I don't know if you can start them. Ah, you did.
Yes.
Fantastic.
Let's see. Mhm.
So we'll spend just 10, 15 seconds. This is there. You're not being graded. It's just testing yourself, and we'll see if hopefully I did a good job of explaining what Flashpoint is.
Yes, we're seeing some answers coming in. Would like to have all of you answer the question. So let's go ahead.
Yeah, take a shot. Don't worry. We won't laugh.
Mhm.
Well, maybe we will. Barbara will laugh. I won't.
No, not at all. But keep voting. Keep answering. I like seeing this.
Yeah. See if you guys have been paying attention for the last 5 minutes.
And this is something you covered at the beginning. Yeah, Flashpoint,
I
which is not the
did.
same
I mentioned
as
this.
ignition temperature.
Yeah.
It's lower than the ignition temperature, if I remember
That's right.
correctly.
I did say that. It's lower, and it's not the same as the ignition temperature, right? So we've kind of
Perfect.
given
So,
away some of these.
yes. Okay, I think we have a good amount of people answering already, so we can end the poll now.
Gonna show the results.
I can share the results.
There we go. Yeah, so a majority of you did say the right thing. It is number B, if you will, temperature in which a flammable liquid will turn into a flammable gas. So that would be the correct answer. Yeah, number 1, or A, on their temperature in which a gas or vapor will spontaneously ignite, is actually called the ignition temperature. That's not the flash point. So, and then the ignition temperature is number C, I guess, the ignition temperature. Well, that's not really what we were asking the question. So, and yeah, we did talk about solids becoming liquids. So well done. Well done. The majority of you got
Good
it
job.
right. So there we go. That's good. All right, moving on. Another thing that we have to take into consideration is the temperature code, temperature classification. So you'll see this on equipment, and you may see this on drawings that will say things like it's a T3 or a T6 or a T4 or whatever that is. And it means different things depending on if it has to do with the environment or the equipment. And so in effect, the T numbers are basically set, and T1 stands for 450 and so forth and so on. And you can kind of read through that. But what it actually means, if you will, is that when we categorize our gases and vapors, and we didn't really talk about gas groups, we talked briefly about that, but not really. We also have to understand what is the ignition temperature of these particular gases and vapors that we're going to find in industry. And we will put these in these 6 different categories and assign them a temperature code. And so in effect, if we look at, for example, hydrogen on there and T1, T1 stood for 450 degrees. Well, hydrogen actually has an ignition temperature, or what we might call an auto ignition temperature, of I think it's 540 degrees. And don't quote me on that, but I think it was 540 degrees C. So what we're saying is that we will categorize this gas, hydrogen, as a gas that has an ignition temperature of above 450 degrees. Now, why that becomes important is that when we start selecting EX equipment, we need to make sure from a temperature standpoint that my product that I want to use in that environment will have a T code that is at least that number or better. So as long as our product has a T1 rating, that means that our product will never exceed 450 degrees. So that's why the T codes mean different things. For a product, it's indicating that the product will never exceed that number. For the environment, it means that that particular environment will have an ignition temperature above that number. So that's what T codes basically mean, if you will. And this kind of puts it together here, if you will. So again, as the example, as you see on the slide, if a product that carries a T4 rating, that means that that product under a maximum ambient temperature will never exceed 135 degrees C. A T4 gas will have an ignition temperature above 135 degrees C, but it's something below the next one up, which is T3, which is 200 degrees C. So in effect, in an environment in which maybe we have a project in which T4 is our benchmark for the gases and vapors, then as long as we use a product that is rated T4 or T5 or T6, we can use all of those products in an environment in which T4 is the project threshold. On the other hand, if we had a product that was marked T1, and we wanted to put it into a T4 environment, well, that T1 product is going to have a relevant ignition temperature, surface temperature, if you will, of something above 300 degrees C and below 450 degrees C, which is much higher than 135 degrees C, which means that we could not use that particular product. So it's an important fact that we look at, we see it, but people don't necessarily understand it all the time. But please be aware of that, because that is part of the criteria in selecting EX equipment. Another factor that goes into area classification is the density of the gases and vapors. So depending on where we're actually located and where the process is, in some cases, we have gasoline, well, generally we're going to find flammable atmospheres down near our feet or down at grade. If we have acetylene has the same density as air. And so anytime if we release acetylene into the environment, it will go up, it will go down. The reason why we need to know density of these gases and vapors is in many cases, we require things like gas detectors to indicate to the workers or into the facility management to say, hey, look, we've got a release of a flammable gas or air mixture or a gas into that air mixture. We need to take actions right now. Well, where do we put these gas detectors? If we have a pressurized building in which maybe there's gasoline vapors nearby that could somehow seep into this building, we would put the gas detectors near the floor. On the other hand, if this same building was located in a facility in which maybe hydrogen was located or nearby, then we'd put our gas detectors near the ceiling. So this is all to make sure that we're doing our design properly. We need to know the properties of these gases and vapors. So this just kind of gives you an indication in a kind of a chart, if you will, to kind of show if we had density of heavier than air, then we might put the gas detectors down in low spots. And of course, if it was lighter than air, then we'd probably put our gas detectors in higher spots. And of course, if the density was the same as air, then we would put them almost everywhere, because wherever air goes, that's where the vapor will go as well. And we have another quick poll question. I don't know if
another poll. Let me launch it.
I didn't go through all of these, but maybe you might remember somewhat or saw the chart a little bit.
So let me remind you guys, T5 is 100 Celsius, right? T4 is 135 Celsius, and T3 is 200 Celsius, in case you didn't remember.
There you go,
The
Barbara, you're
temperatures.
helping.
I never memorize the numbers. I have a poster in my office, a GMI poster in my office with that information.
That's okay. It's fun when we do classes and stuff. Sometimes Wayne, my colleague, will do some of the teaching, and then I may be doing something else, and then I'll come into the classroom, and they may be doing a break, and I'll literally just kind of go into the classroom, and I'll just start asking questions, and they're like, "Oh, shut up," you know. I'll say, "Tell me what T4 is," and they're all
Yeah.
like, "Oh, we just talked about it," and yeah.
Yeah, I cannot remember the numbers, but that's why I have my poster there to remind me
Absolutely, that's
values,
what they're for.
and that's fine too.
Absolutely.
Okay, so let me end the poll so we can review the results.
Yeah. So, Barbara, what would you say the correct answer is? I'll
You're
put
putting
you
me on
on
the
the
spot.
spot.
Yeah,
I'll
I'm
put
gonna
you on
say
the spot.
T4.
Yes. T4 would be the
Oof.
correct answer. And so T4 is 135 degrees C. So if I remove this little poll question from my slide so I can see it. So if the maximum relevant surface temperature of a piece of equipment under normal or fault conditions is 125 degrees, we would mark that product as a T4 because that is 125 degrees C is below 135 degrees C. And in that case, if we had a T4 product, we could use it in an environment in which the gas was a T4 or T3 or T2 or T1. So that's kind of how that all works. So good job. All right, let's see here if I can continue on. And I know we're doing okay on time, but I want to get through some good stuff. So a little bit on area classification. And there's more or less two main uh, topics or concepts that you pretty much can follow, if you will. Um, under ATEX and under the IEC, we follow more or less the IEC or EN version of the 6007910-1 or 10-2 standards for classifying hazardous locations. There's also a document called the Energy Institute, or used to be known as the Institute of Petroleum, IP15 document. That is a wonderful document that a lot of companies over the years have used as far as area classification. Within the United States, we have what are called American Petroleum Institute recommended practices 500 and 505 that are used for area classifications. And we also have what is called the National Fire Protection Agency document 497 that also provides area classification information. These are not an exhaustive list. There are more documents in which specific environments or specific applications will be referenced potentially in various different IEC or API or NFPA documents out there. So this is not an exhaustive list, but these are the main ones. And so what we do, in effect, we break down the probability of a gas or vapor being present into basically under the zone concept under three definitions, if you will. So if it's continuously present, long periods of time, we consider that to be a zone 0 for gas or zone 20 for dust. If it's present during normal operation, but occasionally we would consider that to be a zone 1 or a zone 21 for dust. On the other hand, if an explosive atmosphere is not present, but it can be for very short periods of time, we would consider that to be a zone 2 or zone 22 type application. And I think I'll go into a little bit more on the slides here. Then under the ATEX, we now have incorporated what are called equipment categories. M1 and M2 deal with mining applications. Under ATEX, under the European directives, we now follow what are called one group category 1, 2, and 3. Then we also place next to that a G or D to indicate if it's a gas or dust hazard. Under the IECEX, we do it slightly different. We have three equipment groups, 1, 2, or 3, and then we designate with either an M for mining, G for gas, or D for dust. So it's basically the marking strings when you start looking at products very closely. This is where it gets a little bit confusing. And we'll take a look at a marking string here in just a little bit, and hopefully it'll make a little bit better sense. But you'll actually have a marking string prefix under the ATEX directive, and you'll have some IECEX markings as well. And then why do we say a certain product is suitable for a higher likelihood of a flammable gas air mixture? And it has to deal with the probability or the protection level, meaning that, for example, for zone 0 installations, we require our equipment to have 2 independent faults and still not be a potential source of ignition. When we talk about equipment that's suitable for zone 1, we only allow a single fault. Under zone 2 equipment, we're saying that this equipment is safe during normal operation and it's not a source of ignition. So the level of safety that's built in for equipment and the protection concepts are different based upon what zone you wish to place this equipment into. I think this is our last poll question. I forgot we had so many poll questions, Barbara.
but they are important, and let's see if our attendees are I'm pretty sure they know the answer. They're following through.
Yeah.
So
now, I'll tell you, I'll give you a hint. It's definitely not 4. And the reason why, because now we're talking a dust hazard, and dust wouldn't be zone 1, it would actually be zone 21. So don't anybody answer the 4th one.
Yeah, they're doing pretty good.
So every now while you guys are doing this, sometimes people will ask, when we go through these competency programs, or where do these questions come from? And these are some examples of some of the questions that you would actually find through some of the competency programs and stuff. So, but yeah, they typically go out and, depending on the organization, the IECEX will reach out to certification bodies and ask them questions. They reach out to us as recognized training providers to provide questions for the questions banks, the question banks. Compex, they generally do a lot of that internally, but then we provide suggestions. And so it's always interesting. So a zone 1, it is not present, occurs infrequently, present is frequently or continuously, place where gas vapor is present occasionally.
Ours says B.
Yeah, I think our correct answer, boy, that's kind of a difficult one. Occasionally during normal,
It's
definitely not C. Gas vapor is present occasionally. No, that's it's more frequently. It's not continuous, but it is frequent. So A, yeah, boy, that's a tough one. I'd have to go back to the actual definition, but it's either A or B, that it is an environment. It's not continuous, but it is frequent and present occasionally during normal operation. That sounds more like a zone 2. So that question's maybe a little bit misleading. So
it allows for discussion.
Yes, open for discussion. So fortunately, you're not being graded here. So there you go. So when we start talking about the protection concepts, and by the way, these charts that you see here, this is all from the GMI wall charts. And so certainly reach out to Barbara and she'll be happy to get wall charts out to you. But there's basically 4 major concepts with regards to protection. There's energy limitation, non-sparking, containment, and separation. For dust, we have energy limitation and separation, okay? And to the right-hand side, you'll see those particular concepts, the markings, what zone of use, and what the relevant standards are. So we'll kind of go through that a little bit. So some of the various common protection concepts, and really energy limitation, is really intrinsic safety. And this limits the amount of energy to below the minimum ignition energy of the particular gas group environment. And it's divided up into 3 different ranges based upon fault tolerance, either EXIA, IB, or IC. So something that is rated EXIA is suitable for the most onerous zone. That's zone 0. If it was IB, that would only be good for zone 1 or 2. And then EXIC would be good for zone 2 only. So that's the difference between the 3. When we get into non-sparking, now what we're doing, we're eliminating the arc or spark to occur based upon the design of the equipment. A very common methodology here is junction boxes that may house terminal blocks. So we consider this to be a non-ignition capable box, and we take into account creepage and clearance distances between these terminals and make sure that the terminals are designed in which they shall not loosen up under vibrations, so there can't be any fault condition. So as long as we're using proper terminals, then there should not be any arcing or sparking. Therefore, we do not have to house this in some sort of big cast flame-proof enclosure. So that's the whole concept of increased safety. A big popular one is certainly flame-proof, where now we're taking electrical high power components and we're putting them into cast enclosures. And we're assuming we're going to have arcing or sparking. We're going to assume we're going to have gases and vapors get on the inside of these enclosures because these enclosures will breathe. They will not allow a flammable gas atmosphere to not permeate to the inside. And if we have an arc or spark, we'll have an explosion. Well, these enclosures are designed to withstand that internal explosion. They're designed to cool off the hot flaming gas before it gets to the outside and potentially ignite any gases surrounding the enclosure. So we actually have three different concepts under containment. We have the flame-proof, traditional flame-proof. We also have what is called powder-filled, and there's also enclosed break. So again, they contain the explosions. We use this concept obviously widely for large power enclosures, housing contactors, relays, and various other things. But sometimes you'll actually find things like solenoid valves or small little proximity switches. They will actually use this concept as D, and they're containing it in the explosion within inside this little housing. And then separation is more or less divided up into a couple different concepts. Encapsulation, where we're pouring a resin in. We're hermetically sealed, which is considered to be EXNC. There's also different levels of pressurization, where we're pressurizing a panel. We're keeping a flammable atmosphere outside of the enclosure. We may be immersing any particular electrical or electronic components in oil, which again, removing any potential flammable gas air mixture from coming into contact with a heat or electrical spark. And then finally, restricted breathing, where we're sealing up this particular piece of equipment to not allow gases and vapors to come into contact with a hot surface. So these are all different protection techniques that are all widely used as well. And there's always times where people will come in and we sell products, we do training, we do inspections, and people always ask, which is the best method? And there's not necessarily kind of a one size fits all. But if, for example, if I was doing instrumentation circuits, intrinsic safety, there's some significant benefits for doing that. On the other hand, because intrinsic safety relies on a 690 volt panel board intrinsically safe. We can't make an LED floodlight intrinsically safe. So we just can't use intrinsic safety for a lot of devices. Then it comes down to what zone of use and what protection concepts are available. Do we have instrument air? If we have instrument air, then maybe pressurization is a concept, because now we can put a lot of arcing equipment or PLCs or controls into pressurized panels. So there's not necessarily a one size fits all, but there's certain areas in which you just kind of find, if you will, as you get further and further into it, that maybe you have more options going one way or another. So just to kind of break down a little bit about the marking requirements and what you'll see in a marking string of a piece of EX equipment. So starting on the far left-hand side up at the top, you'll see a CE mark, a 0575. You'll see the EX hexagon. You'll see a Roman numeral 2, a 1, a G. All that is a requirement under the ATEX directive to mark on a particular piece of equipment to tell you that it's in compliance with the directive. So the first two things, the CE, that's telling you in effect it's compliant to some European directive, and there are multiple European directives that is telling us specifically that it is compliant to the ATEX directive. The 0575 number is a unique number that is assigned to any notified body or the certification body that is doing the quality audits. So that number will be identical for the lab every time. So it could be a different manufacturer, but that number will be the same if it was done by a particular notified body. Then we get into equipment group, and we didn't talk about this, but if it's Roman numeral 2, that means that equipment is designed for above ground. If it was below ground, it would be a Roman numeral 1. So assume we don't have anybody here in the mining industry, we're always going to be seeing Roman numeral 2. Then we see a 1G. That 1 is that category 1, which equates to, in this case, a zone 0 environment. And the reason why I say zone 0 as opposed to zone 20, because the next digit is gas. So 1G equates to a zone 0 environment. Then we get into our protection concept marking string, which is going to start with an EX. Then our protection concept, in this case, intrinsic safety, 2 fault tolerant. Our gas group, in this case, it's good for Roman numeral 2C, which infers all gases. And oh, by the way, there's our temperature code, our T4. And then we follow it up with what is called the EPL, or equipment protection level. And that information, that GA, means the exact same thing as the 1G under ATEX. The GA is basically saying it's good for a gas atmosphere. The A is the highest level of protection, meaning it's suitable for zone 0. So if you can remember all that good stuff, that's how you understand these marking strings. Now, you look below, you'll see there's an ATEX certificate number and an IEC-EX certificate number. So the way it works, you see in this case, the top row, BVS, that's the notified body. 14 was the year in which it was issued. It says right there, ATEX, and then it has typically a 3 or 4 digit number, and it may be followed by a supplemental letter. Right underneath that, you have the IEC-EX certificate. Again, it was done by the same organization in the same year. And in this case, this was the 19th certificate that they issued that year in the year 2014, and it had an X at the end of it. So if this product only had ATEX and it did not have IEC-EX, the marking string that you see right above would be the marking string that you would find on the product, and there would not be an IEC-EX certificate number on this. On the other hand, if this product had IEC-EX only and not ATEX, it would not have the directive markings. It would have the standard markings along with the IEC-EX certificate number. In this case, this product has both ATEX and IEC-EX, so they've combined all that into one big giant marking string and included both certificate numbers. So when you're starting to really look at these products and trying to identify what that all means, that's basically what this means. So kind of how do we do it? Yeah, got a little bit of time. So this is a marking on a typical GMI intrinsically safe barrier. And I won't go through all of this, but if you notice on the very top line, you will see a Roman numeral 2, a 3, and then you'll see in parentheses a 1. So what that is basically saying, this is good for a category 2, a category 3 environment, which is in effect a zone 2 environment. However, in brackets or parentheses, we have a 1, meaning that the output from this barrier can be fed into a device that's located into a zone 0 area. And then we see some additional markings, EX and A, and that means that this product can be installed in a zone 2. And then we see, in this case, not parentheses, but brackets with an IA space GA, and that's in effect telling us that we're providing protection downstream into a zone 0 area using intrinsic safety going into a zone 0. And then our gas group T code and where this product. So you actually, in this case, you kind of have a little bit of a combination. You've got a combination of where this product can be installed, as well as information to the field device of which this product is going to be providing protection to. So sometimes these labels can get a little bit confusing, but when you start thinking about the nomenclature and really study it, it does somewhat make sense. And by the way, if you ever really just want to know the whole idea behind the marking, this is all located in the 60079-0 standard, which is the general standard for all EX equipment. And it's all listed in there in the marking strings and the ideas behind that. So here's again a real world situation. Again, we've kind of gone through this, but you can see there's a top row showing its ATEX approvals, and then there's a bottom row showing its IEC EX approvals. In this case, this product has both those certifications on there. And it's good for both gases and dust. It also has an IP code, which we didn't talk about here. And then it also has a TA, which is our temperature ambient. This is one thing I do want to bring up, and it's not within our slides, but here's an important thing to note. A piece of EX equipment does not have to be marked with its T ambient. If it doesn't have its T ambient marked on it, the assumption is it's good for -20 to +40 degrees C. Now, in some parts of the world, it gets above +40 degrees C quite often. It could be +50, it could be +55, in some cases, maybe even +65. Remember, we talked about temperature codes, that's based upon the relevant surface temperature of a particular product. Well, that temperature code is based upon whatever the maximum ambient of this product is rated at. So what I'm saying here, in effect, if you look at that label closely, it says it's a T5 product. Well, that's a T5 rating, taking it up to its maximum ambient of +55 degrees C. So the important thing to note, sometimes you'll look at products and they may have multiple temperature codes. The reason why they have multiple temperature codes is that they may have multiple ambient ranges as well. So you have to identify the appropriate temperature code to the ambient in order to properly select and make sure that if you're inspecting the equipment, make sure it's appropriate. Well, I think we have one more.
Absolutely. Let me do this one.
So this one's a little tough, I will admit. So we talked a little bit about all of that, but it was very brief. So I just take your best guess.
Mhm. And we have a question, Bob, that I think goes hand to hand. So I'm going to summarize it. They're saying that they purchase an EXD enclosure, certifies an EXD enclosure, but they install intrinsically safe barriers that, of course, they are certified an EXE barriers with an output of EXI, right? But
Right.
the marking of the box doesn't say anything about any IS circuits on it. What does that mean?
Yeah, so it is supposed to have a marking. Actually, what you see right there in that marking string is the way that box should be marked. It should actually be marked EXD or DB now, which is indicating a flame-proof enclosure. We have in brackets the IA, which is our output, and that should be marked on the overall label of the enclosure itself. Now, I will tell you, in the real world, some people, they don't really realize that, or some companies are like, well, we're just putting IS barriers on the inside of a flame-proof box. We can put, all different kinds of products on the inside of a flame-proof box. What I would do in that scenario, what is a requirement, is that if I do have intrinsically safe barriers inside of a flame-proof box, I absolutely am required to have a label put on that box that says contains intrinsically safe circuits. And we also have to make sure that there is a separation between our IS and non-IS inside of that panel. And it's at least 50 mil. And we typically, if we have IS terminal blocks, we would typically use blue terminals. And we'd want to make sure that we, again, if we have some ducting work on the inside of that, we would probably use blue duct versus our standard gray duct. So there's a couple little things there that, but generally speaking, yes, the flame-proof product should have a certificate available that they will have a box that will be marked DB, and a fully assembly certified box with a DB marking will basically, looking at the cert, will reference traditional control devices. Then they may have a separate cert that will be EXDB brackets IA. And that's basically saying we've got that same exact enclosure and you can put the same control components and you have the ability to use associated apparatus on the inside of this enclosure. So it's not a different box. Typically it's going to be a different certificate. And then certainly the marking on the box, on the outside of the box, the labeling will have this additional information.
Perfect. Okay, so I think the majority of our attendees responded this question.
Yeah. So yeah, let's see what the correct one. So it is a flame-proof box, and it looks like it's either A or C is the majority. So is the box suitable for 2C? Yes, they're both suitable for 2C. Gas is located in a zone 1 area. The first one, yes, it is a flame-proof box that is located in a zone 1 that does contain associated apparatus. The flame-proof enclosure C, flame-proof enclosure is suitable for 2C gases, which is true. Containing increased safety relays suitable for zone 0. No, it's not increased safety relays. It's actually, in this case, an intrinsically safe associated apparatus suitable for zone 0. So the correct answer would be A.
Good. And the majority of our attendees got it right.
Yeah, that's a good one. That's a good one. If you know that, you know a lot. That's fantastic. So a couple other things, and then we do have a couple Q&As just to go through those real quick. But there are some other wall charts that GMI has. If you're involved in functional safety, we have some wall charts on those. And certainly, the key thing that we always want to remember, I didn't really talk about this, about the 80079, but the whole idea is the more knowledge that we can gain in the whole EX world, I think, it just makes our industry safer. And it's always important to make sure that, no matter what role we have in this whole thing, whether or not we're in design or engineering or installation or procurement or whatever, always try to make sure this is a safety critical industry. And again, it's the weakest link, right? Where mistakes happen, if it happens here, then all of a sudden it takes place over here. So we want to try to, catch any of these issues before putting lives at danger. And again, dust hazards are as dangerous as gas hazards. So let me do this. I'm going to stop share for just a second. And then.
Did you want me to share the question and answer?
Well, I think I can.
You have it there?
I do, I think. Let's see if I can do it here. I'm going to share. Let's see. I think this is it. Is this it? No, that's not it. I apologize. Hold on. Let me
Almost there.
Almost there. Okay. Fundamentals EX Q&A. I just have to I have to make sure I bring up the right one. I think this is it. Is this it? Okay, I think you're seeing probably
your PowerPoint.
The PowerPoint, and then is this, so did I just Oh, I did wrong. Why don't you do it, Barbara? Because I'm screwing up here.
Let me try. Okay, let's see. You guys see that?
There you go. Yes, I see it.
Perfect.
And we don't have many more slides to go, so we'll just. So a non-electrical equipment valves, I see some that have ATEX marking, others that haven't, but apparently are still safe to use. So yeah, it's a good question that does come up because there is mechanical standards that are out there that have been published, and they started off originally as EN standards and now have been adopted as a joint ISO IEC standard. So certain products such as couplings, pumps, gearboxes, brakes, hydraulic and pneumatic motors, uh, they fall under the scope of the ATEX mechanical requirements as well as the IEC requirements. Certain things like hand operated valves do not fall under the scope, but things that are mechanically driven are issues that are something that we have to consider. I think somebody was knocking on my door. My maid. What is the minimum training does a certified North American journeyman must have to meet EX competency? The minimum requirement under the COPC or Compex schemes is generally about 3 years in the field of EX. So you should have been doing some installation before you come into those programs. Within the US, the Code of Federal Regulations do not require any proof of competency. However, some organizations at the federal level, such as the U.S. Coast Guard, are stating that wish that they do see these people who are responsible for safe installations. And both the Coast Guard and BSEE, the other federal organization that's responsible in many offshore installations, are now starting to realize that they want to see competent people doing these electrical installations. So we're seeing a lot more demand. We are seeing it here in the United States as well. Seal tape. This comes up every now and then. So to make a flame-proof product a little bit more watertight, there is a passage within the standard. You can actually use a non-hardening grease. Well, actually, it's always good practice to use a non-hardening lubricant on the face of these enclosures. But it's also a process in which we can take a tape, a single roll of what is commonly referred to as maybe a Denso tape, and we can actually wrap that around a flame-proof flange to provide a higher level of water protection. However, most of your flame-proof boxes now do have an integral O-ring that's built into the flange or to the threaded cover that provides a level of protection. So generally not needed, but it certainly can work. This is always a big question. Differences between the US and Canada. So both the US and Canada, we do have our own electrical codes and practices. However, both the US and Canada have a standards, but it's more for a product specific design standard, not necessarily installation standard. So sometimes people will ask the design installation standard in the IEC world or in Europe is the 60079-14 standard. That's not going to get adopted here in the United States or in Canada because we already have the National Electric Code here in the United States and the CEC up in Canada. So instead of adopting the -14, what happens is that a lot of the concepts that are within the design standards are actually adopted as potential design criteria within our own set of installation and design details. So the other thing is that within the US, just bringing over a product and using it in the United States that only carries ATEX or only carries IEC EX is generally not allowed other than the offshore market where the US Coast Guard has specifically stated that IEC EX is acceptable. However, products that have to comply with the class and zone requirements have to undergo additional fire and shock hazard testing. which is not a requirement under the IEC EN standards for hazardous locations. So there's an additional testing requirement that we require in the United States. Can I install an intrinsically safe barrier in a zone 1? Yes, we can. So if you noticed when we showed that label on the intrinsically safe barrier before, that barrier itself was rated for zone 2, but if we needed to put it into a zone 1, we would have two choices. We can install that barrier inside of a flame-proof enclosure, or we can install it inside a pressurized panel that was rated for zone 1. So sometimes that does happen where maybe the cable length is very, very short between the intrinsically safe barrier and the field device, or we need to make it very close for whatever particular reason. This is an option. And that is us. And I think they're banging on my door again.
Yeah. So yeah, absolutely. We appreciate everyone attending today. We do have a few more questions on the Q&A. We'll answer it via email during the week. And any suggestion for next topics, please feel free to email it to us. And thank you so much for everyone's participation today. Thank you so much, Bob, for the valuable information you shared with us today.
And I'm sorry I didn't get a chance to answer all the questions, but yes, please reach out to us and we'll try to answer the questions offline. And again, thank you so much for spending time with us today. And thank you so much, Barbara, for all the hard work you're doing.
My pleasure. Have a great day, everyone.
Okay, bye-bye, everybody.